Okay, so we will next look at compensator design by the separation principle. This is what is discussed in Friedland chapter 8. Now, once again, here's the plant differential equation and the plant output equation, and this is the control law if we now limit ourselves once again just to a regulator. I'm going to talk just about regulators now. This is the control law that we ideally would have liked to implement, where we calculate the feedback gain matrix that pre-multiplies the states of the physical system. But we've now already conceded in chapter 7 that we cannot actually implement this control law because all the state variables are not known. And because of that, we derived the Lunenburger observer, which is given by equation 7.8, and it's repeated in chapter 8 as equation 8.4, given by this equation, where our observer then is a dynamic system that uses the same input that goes to the plant and the output of the plant to calculate the estimate of the state variables. And this then leads us to the actual control law that we are going to implement, namely that the input is the G matrix times X caret. So in this, the G matrix that we're going to use here is the same G matrix that we've designed in chapter 6 with the assumption that all the states are known or measurable. But the actual states that we use is the observer states, X caret. By the way, if I were to use a reduced order observer, then in that case this vector would really need to have a different name, because then part of the vector will be the actual states and other parts of it will be the observer states. But okay, let's not go there now. Let's limit ourselves to the case where I use a full order observer. So all the states that I use in my control law are then the states coming from the observer. Now, we designed our feedback control, in other words, the selection of the gain values in the matrix G. We selected that to have favorable plant dynamics, or to change the plant dynamics from the way it is in the open loop case to some other better characteristics. That's the whole point of having this full feedback design, is to improve the plant dynamics. And we did that by placing the poles at the most favorable locations. By the way, I actually neglected to mention this morning, the question of what is the most favorable positions is also a question that one can debate, and Friedland does actually spend a little bit of time in the book in chapter 6 discussing that, so please take note of that. The fact that I haven't spoken too much about it doesn't make it uninteresting or not important. And this issue is also addressed again next time when we get to the optimal control theory. But in any case, assuming that we know where the most favorable positions in the X-plane is to place our poles, we've now designed our plant to have that characteristics. And we've designed our observer so that it's fast, and so that the error between the observer and the observer states and the actual plant states go to zero very quickly. But we've designed these things as if the one is not affected by the other, as if it's two completely separate designs. And yet through this very control law, we couple them. And so now the question is, well, don't we now mess up everything when we do this? And that is what we'd like to now investigate. What is the effect of then applying this control law to the nice properties we achieved by setting our design, our plant dynamics? And by the way, here already you can see that the plant dynamics now already contains this X caret through the control law. But by doing that, don't I negate all the gains I've made in actually doing the pole placement design of the plant, and then likewise for the observer? Now, these two equations are just repeated here. If I now, as before, as in chapter 7, define the error state as the difference between the plant state vector and the observer state vector, and I then substitute, I write x caret in terms of E and X. In other words, x caret is X minus E. And I substitute that into both these equations. The first equation, the plant equation, changes to this. And you can check the mathematics. So equation 8.8 is the resultant equation when I replace x caret using this equation in equation 8.6. And equation 8.9 is the resulting equation that I get if I do the same with equation 8.7. So in doing so, I've changed my two differential equations, that of the plant in the closed loop system and the observer, into once again a plant equation, but one that doesn't contain the observer states. It contains instead the error state and just an error equation. And now I can put these two equations in a matrix. I think I'll repeat this on the next slide, most probably, yes. This is just the same equations as on the previous slide, but this can now be placed in a matrix form like this. The two left-hand sides. Now note that the vector x and x dot and e and e dot are all of the same length, namely of length k if I've got a kth order system. In other words, if the A matrix is k by k. So on the left-hand side, I've got the time derivative of a 2k by 1 vector. And on the far right-hand side, you can think of this as a state vector, also of length 2k, and then this is almost like a new A matrix for a system of double the size. Now, this is actually true that the moment I put the observer, I connect the observer and the plant with a control law that I'm using. If I have a full state observer, I'm actually doubling the order of the whole system. In other words, if my plant was 4th order and I use a full order observer, I now have a 8th order dynamic system that I'm operating, if I can call it that. My whole control system, plant and observer, is then 8th order. And that is quite clearly reflected by what I'm doing here. My new A matrix is this matrix, and it's 8 by 8. Now, of course, if I've opted to use a reduced order observer because some of the states are available directly, let's say once again I had a 4th order plant, but two of the output made it possible to actually know what two of the states are, and I, because of that, opted to design a 2nd order reduced order observer, but that is 2nd order. In that case, my new A matrix will be 6 by 6 and not 8 by 8. But let's for now stick to the full observer case. So I've got this 8 by 8 matrix. Now, remember the question that we want to answer is, well, have we messed up all the nice properties that we've designed into the system? That question will be answered if we calculate the eigenvalues of our new A matrix, right? So that's what we need to do now. We need to calculate the eigenvalues of this matrix, which has a submatrices, two diagonal submatrices, is the AC, which is A minus BG, the old one that we've seen this morning in chapter 6. A caret, which is A minus KC, and then there's an off-diagonal submatrix, which is BG, and the other off-diagonal submatrix is a zero matrix. So if it's a K by K zero matrix. These 4 submatrices are for the case of a full state observer. The 4 submatrices in this bigger matrix are all of the same size. Okay, so how do we calculate the eigenvalues of this matrix? Because that's what we need to do next. It turns out that, and this, by the way, is not actually in Friedland. Friedland argues this once again in a Laplace domain argument. He converts this to the Laplace domain, and then he offers a Laplace domain argument to get to the conclusion where I'm heading now. So because of that, I decided, well, look, we want to stay away from the Laplace domain. I'd like to do this in the time domain. And because of that, I've written a set of theorems in the set of notes, comch8.pdf. You'll find, I think there are 4 theorems there. And the second theorem in that set of theorems actually proves that the moment you calculate the eigenvalues of a matrix of which the off-diagonal, a matrix where the submatrices are of same size, and one of the off-diagonal submatrices is a zero matrix. So in other words, either this one or that one. If either of those matrices are zero matrices, then the eigenvalues of the whole matrix is simply the eigenvalues of A sub c and A caret. Or in other words, the eigenvalues of the whole matrix is then simply the eigenvalues of the 2 diagonal submatrices. And so this is wonderful news, because it means that by employing this control law, we have not destroyed the favorable properties that we've designed this morning. We placed the poles in choosing the G matrix with pole placement. We placed the poles of AC at the favorable positions, or the eigenvalues of AC at the favorable positions. And in designing K with the pole placement of the observer, we've placed the poles or the eigenvalues of the A caret matrix in the favorable positions. And once we then couple them together with this control law, we do not destroy that, because the combined A matrix has the same eigenvalues, namely the eigenvalues of A sub c and the eigenvalues of A caret. And this is called the separation principle. The separation principle basically states then that I can design my feedback control system as if I do not have an observer. And then I can design my observer as if I don't need to care about the feedback control system. I care about the plant because I use the plant A and B matrices and C matrices in my observer design. But other than that, I don't need to worry about the plant. I can design the observer on its own. And then I can combine the two in a single system without destroying the properties of the system that I've designed in this way. That is the separation principle. So this is really what I've already just now said, these 2 points. Of course, the implication is this third bullet here, that if we use the observer and the full state feedback be careful now. This full state feedback only refers to the feedback, not to the plant, but the feedback that was designed for the plant. If we combine the observer and the full state feedback as a compensator, the result is that provided that the observer contains an accurate model of the plant, the overall system will also have favorable dynamics, namely the favorable dynamics that we've designed. So this again touches on the issue of robustness. The observer should be an accurately modeled plant. That is discussed on page 301. You can look at that. Now this is an important point, and I'd like to stress this because I'm specifically asking you this in the 2-car train assignment that you now have. Do not confuse the compensator with the observer. So for this, I refer you to figure 8.1 in Friedland. So let me just show you the figure. So this nicely shows what we are doing here. And by the way, this is now only for a regulator. In the 2-car train problem, I'm asking you to draw a block diagram for the case where you do not have a regulator, where you have got a tracking and disturbance system. So then you'll have to, in a certain sense, modify this block diagram. But look at this. These dashed lines indicate where's the plant. See, there's the plant differential equation as we originally had it. The output of the plant Y is fed back as an input to the observer. Now the observer, I'd like to draw a red rectangle around the observer here. That is the observer. Remember, we said from the beginning, the observer takes two inputs. It takes as an input the output of the plant, but it also takes the input to the plant as an input. And the output of the observer, well, the observer doesn't really have an output, but the observer estimates the states that's used in the control law. This part here is the control law that says that U is equal to minus G times X caret. But if I talk of the compensator, it's more than just the observer in the sense that it then includes the feedback control gain. And that is why the compensator boundary is there. Think of it like this. The compensator is really this what you as the control engineer add to the plant in order to control it. And because of that, the compensator needs to include the feedback gain that we've designed in chapter 6. And so when we now define the compensator as this wider block, wider than just the observer, we note that even though the observer had two inputs and one output, the output being X caret, it's not really output in the state space sense of the word, but it is actually output in that it's a signal that goes out of the compensator, out of the observer. The compensator has only, for the case of the regulator, the compensator only has a single input, which is Y, the output of the plant. And it has a single output, which is U, the input to the plant. Okay, so take careful note of this. Okay, now, the regulator system compensator is also a state space system with, as I've just now said, the input Y, the output U, and the state variable X caret. In other words, the compensator state variable is in fact the same as the observer state variable. That doesn't say that the compensator is the same as the observer though. It does have the same state variable. And the state differential equation is not this equation 8.7, but it can be derived from this. Friedland doesn't actually write it down, but you need it later on. So because of that, I'm writing it down on the slides for you. If I rearrange Friedland's equation 8.7, I actually get this equation. And I'd like to add another equation to this, namely this one. If I look at these two equations, I'm claiming that these two equations are the standard state space representation of the compensator, because what is between the square brackets here is the A matrix of the compensator. K, the gain matrix of the observer, is the B matrix of the compensator. And minus G is the C matrix of the compensator, because the compensator output is minus G times its state vector. Right? So this is our standard state space representation of the compensator. And it turns out that if you now want to implement a controller on a computer, or let's limit ourselves to a digital system, then you need to create this state space system. You need to create in the computer this state space system. You're going to take the output of your physical plant and you're going to plug it into the computer through an analog to digital converter. It will measure the output Y of the plant, which is the input to the compensator in the computer. And you're going to do the number crunching in the computer, however you're going to do it. We'll discuss that next time. And your number crunching will spit out the output U in digital form initially, and then you'll put it through a digital to analog converter to get it as an analog signal that you're now going to drive the plant with. Yeah, well, inversion is perhaps not the mathematical, it's not mathematically the right word, but I understand why you say that, yeah. Okay, so it's important to then realize this. Now, by the way, Friedland in chapter 8, he actually, I think I have that on, let me just check, I think I have that on a slide. Yeah, yes, right at the bottom. See the derivation of the transfer function of the compensator minus ds. That Friedland, even though Friedland doesn't actually write down these two equations in this form, he does discuss it, but he discusses it in the S-plane, unfortunately. And in doing that, he actually derives the transfer function of the compensator, and he calls that minus ds. And this is shown at the bottom of page 294. So please just take note of that, and when you do, keep in mind figure 8.1, that is now this figure that we've discussed a little bit earlier. And I think this is then basically the story for today. Let me just make sure. Yeah, that's the last slide. So let me then, let me first invite questions. Are there any questions? And let me stop the recording.